I have the privilege of introducing Dr. Andresen. Dr. Andresen is the state of Michigan's climatologist, and he actually gave us a little preview last night for some of you who may have attended the session last night, the public session, and gave us a little preview into his talk. And really, he's going to focus on some of what we're seeing in terms of weather changing and what we're seeing in weather events recently and how that could impact the communities, and more importantly, how we should be thinking about that as we develop our master plans and our comprehensive plans and ultimately look at regulations or standards that the communities may want to put in place to help us adapt to what we've seen. And a little bit more about Dr. Andresen. He's an associate professor of geography with Michigan State University. He is an expert on the weather, especially as it relates to agriculture and its impact on agricultural production. He's also an bioresearch scientist and serves, as I stated, as the state climatologist. So with that, I think he'll have some interesting facts and maybe explain why we have these strange rain patterns lately. So thank you. Dr. Andresen.
Well, thank you, Alan, and thank you again, as Joe mentioned, to be spending a morning on probably one of the nicest real spring mornings we've had thus far this season. It's a pleasure to be here. Looking at the program today and thinking really about the future and planning and building resilience, it's critical to know what are we planning for. And I'd like to start off that discussion a little bit by looking at climate, and I will start with the distinction between weather and climate. Both of those are critical to what we all do here and what we plan for, but weather is the short-term variant of the same variable of climate. So climate is simply the same variables averaged over some period of time. And I'm going to talk a little bit about both, but especially about climate because it's important. One of the take-homes here today is that as we look at the future, what we're really looking at, we're shooting at a moving target. And as much as we like to think of climate as static, unchanging, or stable, in reality, it is constantly changing. It's changed dramatically in the past. It's changing now and will change undoubtedly in the future. And of course, there's a human element now that we're dealing with, and that adds another degree of complexity. So given that background, I'll talk about changes historically that we've observed both here in the region, also look broader globally as well. What's projected for the future? I want to say something about climate variability and extreme events. Very, very important, especially in the planning process. And then finally I'm going to actually I'm going to talk about impacts because many of these changes, many of these types of events have major influence on what we all do, certainly what we plan for. Historically, if we look at our instrumental record around the world, we have about 150 odd years. There's some cases there's 200, but believable and reliable records globally about 150 years, about a century and a half of temperature records. This particular diagram start with, and you're going to see several like this. We have the year on the horizontal axis, and then change or temperature here is on the vertical axis or the y-axis. And for this particular graph, each of these individual years is a global mean average. So this is only for all of the best quality records around the world that have been put together and averaged. And each year is expressed as the difference between the average that year and then a long-term 100-year mean. That's 1901 through 2000. These bars on each of these points are actually confidence intervals based on what we know about how the observations were changed. Technology's changed, obviously, in how we take temperatures and how we observe temperatures over time. So that's what these bars reflect. But I think the thing to note here is that, first of all, if a value is negative, it means that that individual year was cooler than that 100-year average, while positive values indicate, of course, warmer than normal, or warmer than the average. And this blue line here maybe is the most important thing. That's a 9-year moving average, basically to filter out some of those individual year-to-year changes. A lot of noise as we look on a year-to-year basis. And this reflects essentially decadal type of swings and changes. You're going to see several of these in this. So what we can see globally, what we know, the best information we have on the Earth's surface temperatures have warmed overall a little less than 1 degree Celsius or a little less than 2 degrees Fahrenheit on average. That doesn't sound like much, but when we look at how large an area that we're talking about and for the time frame that we're talking about, that's actually a fairly significant change, especially by what we know geologically. There have been two major areas of warming or periods of warming from about 1910 to 1940, and then again from the 1970s up to the present. And you'll see that here. I'm going to shift now to closer to home. This is overall for the state of Michigan. If we throw all of our records together, I'm going to start this series at 1895. We don't have quite as long a record as they do is available globally. This goes up through the end of last year, 2012. The inset note here, this is the southeastern climate division in Michigan, about an 8-county area down in the southeast corner, of course, that includes the local area. They're very, very similar, actually, the southeastern lower Michigan with the state of Michigan. But overall, what you can see in this particular trace is that temperatures from really the beginning of last century through about 1930 were flat, with little change at all. There was a cooling trend then that began in around 1930 and proceeded through about 1980, about 1 degree Fahrenheit, and that's been followed in turn by a rapid or more rapid warming in the last 30-odd years of about 2 degrees Fahrenheit. Now, the interesting thing, and a very, very important thing to note about this last 30-year period here, much of this warming is seasonal. And most of this, if you look at the actual statistics and the arithmetic that goes into those averages, most of that change is occurring in the winter season, to a little bit lesser extent during the spring, and even more importantly, it's at night. Yes, daytime maximum temperatures are increasing, but nighttime temperatures are increasing more quickly. So the diurnal range, the change in temperature on a given day, that's also decreasing. There are some changes during the fall and during the summer seasons, but they're relatively less than what we've seen during the winter. And in some parts of the Great Lakes region, this is really one of the most impressive trends that we can find climatologically. Nighttime minimum temperatures during the December, January, February, the winter time frame have increased as much as 10 degrees Fahrenheit, just in the last 30 years. That's a huge change, very, very large change. And we're going to see a number of related trends that relate back to that as well. There are a number of them, and most of them have impacts, direct impacts on us, the society. One of them, without question, is the amount of ice on the Great Lakes and the duration of ice cover on the Great Lakes is decreasing, unquestionably. This particular series is taken from a satellite series. It starts in 1972, goes through 2011, and basically from satellite we're integrating all of that ice on the Great Lakes. This is actually the maximum coverage. You can see that it peaked back in the late 1970s, and for those of you who are old enough like me to remember the 1970s, there were a series of very, very severe winters during that time frame, and that correlates well with this peak in ice coverage. Lake Michigan froze over, completely over, during 1977. That was in this particular year. But since the late 1970s, you can see with some noise here, basically the trend has been downward, unquestionably. And if we included last year, 2012, there was virtually no ice on the lakes last year. There was a little bit this year, but still much less than the long-term normal. So the amount of ice on the lakes is decreasing. Water temperature of the Great Lakes is also increasing. Lake Superior, for example, has warmed 5 degrees Fahrenheit just since 1979. That's a huge change. There also have been changes in seasonality. This is a confusing diagram. It's called a spaghetti graph for reasons you can probably figure. There are 3 different series on this graph. Again, year here is on the horizontal axis, and the days are on the vertical axis. And what this is, it shows or illustrates changes in seasonality. I'll start here with the green series. This is the change in the relative change in the day of last freezing temperatures during the spring season. And over time, you can see that there's quite a bit of noise here early on in the record. If I can get my cursor back, there it is. Up to the 1940s and 50s, you can see then relatively, still flat, but around 1970, 75, we have a drop-off here as that last freeze of the spring gets earlier in time. And so now, recently, this is a regional average. The last freezing temperatures of the spring are coming several days earlier than they did in past decades. The blue line here, almost the same thing, but we're talking about the fall season, first freezing temperatures of the fall, and what you can see there, that's coming relatively later than it has in the past. And then finally, the red series here, that's the number of frost-free days in between that last freeze of the spring and the first of the fall, and it's increasing. It's getting longer, and so regionally here we have essentially about a week to a week and a half longer frost-free growing season than we did just 30 to 40 years ago. We have looked at this in more detail in Michigan, and what I would say about this is a regional average. In Michigan, we found that it's not symmetrical. There's relatively more change taking place during the spring season. So the onset of spring is coming significantly earlier. We're getting a little bit of a delay in the onset of fall, but it's much more that growth and frost-free season is during the spring. And that was, well, there's an exclamation point on that particular trend last year. For those of you who I'm sure enjoy fruit in Michigan, that's I didn't grow up here, but one of the things I quickly appreciated about living in Michigan is the presence of, especially in the fall, fresh fruit. Of course, that was an exception last year because of an unprecedented, basically a record-breaking heat wave that we had during March of last year. March of 2012 was by far the warmest March on record, going back more than 100 years. 13.8 degrees Fahrenheit above normal. It shattered the previous record by more than 4 degrees Fahrenheit. It was actually the largest departure of any individual month I've ever seen in my professional career. The thousands of records were set nationwide, and 25 states set records for the all-time warmest March, including Michigan. Well, what that did, if you are a perennial plant, like a cherry tree in this particular case, apple tree, you basically respond, your growth cycle, your growth and rate of growth and development respond to changes in temperature in the environment, and each spring these crops come out of their dormant states, and the problem with that is that as soon as that growth and development begins, the resistance to cold drops off dramatically. It's relatively rapid, so a tart cherry tree in full dormancy can handle temperatures of -10 to -15 Fahrenheit without much difficulty. But when it begins growth and development and reaches this so-called side green stage, which you see here down in the lower left, the damage threshold goes way up. It's to the mid or upper 20s Fahrenheit. And of course, last year with that incredible March, warm March that we had, that was followed by 15 to more than 20 freeze events during the months of April and May, and it completely decimated almost all of our fruit crops, less than 10% of normal production in the state of Michigan. It was a terrible year. This particular graph here illustrates that change. I talked about changes in seasonality. This is the day of each year that tart cherries reach this so-called side green stage where they become vulnerable, and you can see that historically this is the calendar day. So day 120 is at the end of April, and you can see that historically back at the beginning of last century and for the first several decades of last century, it tended to occur near the end of April. That got a few days earlier during the 50s, 60s, 70s, and then in 1980 it became even more early with time, and here is 2012, down here in the right-hand corner. The earliest bloom for most fruit crops. Fruit's been grown commercially in Michigan for 150 years, and it was the earliest record of that happening on record. This is a direct result of some of the trends we just talked about. Milder winters plus an earlier start of spring, and this is one very, very real impact, especially for the fruit industry of the state. There have also been significant changes in precipitation. This is looking at the same time frame as we did for temperature, 1895 through the end of last year. And with the moving average, you can see here that Michigan, became a bit drier at the beginning of last century up to the 1930s. The 30s are the driest decade that we have on our historical record. That's true across much of central North America. But ever since the 1930s, Michigan has become gradually wetter with time. There are a couple of exceptions in here, one being the late 1950s and early 1960s, and another, go back here again, another period here in the late 90s and early 2000s, which was a little bit drier. But overall, precipitation has increased on an annual basis somewhere on the order of 10 to 15%. Depending on where you are in the state, that translates to somewhere on the order of maybe 4, even 5 inches of extra water each year that we have now versus just a half a century ago. The inset down here at the lower right is the Climate Division 10, again for southeastern lower Michigan, very, very similar to what we have for the state average. So Michigan has become both warmer and wetter. Now, in contrast to temperatures, this is not nearly as seasonally specific. The increases in precipitation we see here have taken place basically in all seasons, maybe to a little bit less extent in the fall. So as we look at this, and we look at causality, there are 2 ways you can get more annual precipitation. One of them is just to have more days with precip, more wet days, and that's what this next graph is. That has definitely increased with time. This one goes from 1930 through 2010. It's for a representative site in Tuscola County, but it's representative of the state. The blue line here you see down here, this is the annual fraction of days with measurable precipitation in a given year. And you can see that that's increased significantly over time. In the 1930s, it used to be about 1 out of 4 days had measurable precipitation. That's increased to now more than 1 in 3. So there are more wet days. And we don't have reliable records on solar radiation, but without question, if we have more wet days, it's also become cloudier. So that's another trend. The green line here on the top, that's the number of wet days which follow wet days, so multiple wet day events. Those are increasing as well. So that's one part of that increase. The second way to increase the precip is we have more extreme events. That's also increasing. On the upper right here is a chart that looks at the sum each year of the top 10 largest precipitation events in a given year. And basically whether that sum, it's increasing or decreasing. Red circles here are increases, blues are decreases, and you can see for most of the Midwest, the number of this sum is increasing. We are seeing an increasing frequency of those extreme events. Which brings me to basically at least a reflection on climate variability, because we think about climate variability, especially extreme events, droughts, tropical cyclones, storms, you name it, hailstorms. These events are a very, very small fraction of the total fraction of events, or the total sum of events. But they play a huge role because they are responsible for a significant, sometimes a vast majority of impacts. And we really have to be concerned with them. The issue is that, especially as we look into the future, our ability to discern what happens to the occurrence of these extremes and variability is significantly, or at least relatively less than it is for looking at changes in the mean state. And very, very important because historically, we know humans have been able to adapt or cope, in some cases very well, with relatively stable changes in their environmental conditions, including climate. But if you change variability, it makes adapting much, much more difficult. Engineering a solution becomes a great deal more, and some people would say, in some cases, it becomes almost impossible. We won't use that word, but it certainly becomes much more difficult. Historically, there have been increases in the number of extreme events across the Great Lakes region. Again, this is a regional sum. This is an index, an empirical index, which looks at extreme temperature and precipitation events combined. And you can see that there was a relatively low period of low frequency of extremes here during the 40s, 50s, 60s, and into the early 70s, but it's basically been increasing ever since. Now, I would say that this particular index, most of this increase, taking apart what the index is actually based on, most of this is increasing extreme precip events, heavy rainfall events. That's where most of that increase is coming from. Here's a caveat to throw another little bit of a confounding factor in here. This is a trace from 1980 through 2010 of worldwide weather-related disasters and basically the economic losses, which are overall losses are in orange, and the blue line, the blue parts of those are the insured losses for that given year. You can see that in most cases, most of the losses associated with these weather disasters are not insured. That's a scary thing. But, by the way, this is all converted into 2010 dollars, so inflation's not playing a role at all here. There's no back trend of the value of the dollar. This is in 2010 dollars. But unquestionably, there is an increase in the amount of loss each year with time related to weather disasters. Now, the big question is here, and it's an important one, is this because of an increase in some of these weather events, the extreme events. Most of the top two here, above all, of the types of events, without question, are tropical cyclones, hurricanes, typhoons, depending on what part of the world you're at, and droughts. Droughts are much larger, they're much slower to develop, they take place over, though, a much slower time frame. The drought of 2012 in the U.S. right now, the estimate of damage is $50 billion in climate. It will be one of the top three in the U.S., and again, it didn't happen overnight, it took time for that to develop, but economically it's certainly no less important. But the point here is about what's behind this. There have been a couple studies on this, and the conclusion was that, well, in some parts of the world we are seeing a bit of an increase in these extreme events, but in some places we're not. And so then the question is, well, how do you explain then this increase in losses? And the answer is, we as humans, we have more stuff in the way. I mean, to put it very, very bluntly. There's more there to be damaged. And so this is something to think about. I think it has to be added to the equation. We're more vulnerable as a society than we were decades ago, and I think this is evidence of that. Let's look into the future here. What do the model projections say? And this is taken from the Intergovernmental Panel on Climate Change. Basically the best estimate, scientific guess of where things may be in the future, given a number of different scenarios. On the top here, basically we have a low greenhouse gas emission scenario. On the bottom, there's a high greenhouse gas emission scenario, but collectively what these say is that by the middle of this century, temperatures here in the Great Lakes region will warm something on the order of 2 to 3 degrees Fahrenheit on average by the middle of the century, and as much as 4 to 11 degrees by the end. Now, again, that doesn't sound like a whole lot, but that's a very, very large change. Note also that there are definite regionality to the changes themselves. Interior areas of the continent are projected to have the largest changes, where the coasts, where we have the buffering capacity of the oceans, reduce that change a little bit. Now, as an analog, and this is a very, very simplified way of looking at this, it's actually too simple. This is a very complicated issue, but if temperatures did warm 4 to 11 degrees by the end of the century, if we looked at that in terms of a current analog of climate, we'd have to go down to the middle or lower Mississippi Valley, even the southern Great Plains, to find a climate that was that much warmer. Again, that puts it in a little bit different perspective. This is a very complicated projection, and this is simplistic, but it does give I think, some perspective. Not only are the means expected to change, but the number of, extreme events, the days above 95 degrees, for example, the length of the frost-free growing season, and the amount of cooling degree days, which is basically a measure or a proxy for how much cooling we need during the summertime. All these are projected to increase. This is for the 2041 versus the 2041 to 2070 versus relative past. All of those are forecast to increase or projected to increase. Some are already increasing right now as we speak. We've shown evidence of that already. Which brings me to another conceptual idea here, and this is an important one for planning, very, very important one, and that is the nature of the change itself. We talked about climate as being a changing entity. How does that change manifest itself, at least statistically, as we look out and plan for the future, whether it's trying to figure out how much we need for a combined sewer overflow, how much draft depth do we need to have in a harbor? There are all sorts of questions we have about how climate might influence the future. We need to look essentially at this statistical distribution of events. And I'll use temperature because it's probably the most simple and straightforward, and it is relatively symmetrical or Gaussian, just like the tops suggest here. But the question is, how does that change take place? Do we simply pick up the distribution and shift it along with the tails and the extreme events that are in both ends? That's the simplest way of looking at that. Or do we have to deal with changes in variances, the extreme events, including the extreme events frequency, or do we have to look at both? And from what we've seen, the illustration here on the right is actually looking at the last several decades, and it's looking at the ratio of high and low temperatures. High temperatures are in the red, blue temperatures are in blue, and you can see that there is a gradually increasing fraction of record high temperatures being set. Empirically, for the past, we can say with some confidence that that shift looks a little bit like that top graph. So we are seeing a phase shift of temperature. Now with precip, it would be more difficult because, for one, it's not symmetrically distributed. It's a little bit more complicated. But so far from what we can tell historically, we appear to be seeing this. We're not seeing as much change in the variability. That's very, very important. What happens in the future is another question. Some of the early work that I've been involved with looking at this also suggests a bit of a symmetrical phase shift. But a lot more research has to be done with that. Hopefully, we don't end up with the bottom one here where we have to look at changing variability. That's even more difficult to project. Let's look at precipitation and what's forecast or projected for the future. And overall, annual precipitation in Michigan and the Great Lakes region is projected to increase. But a very important caveat, most of that increase, areas in blue here are increases, areas in brown are decreases on this map of North America. Most of those increases are projected to occur during the cold season, during winter and spring, but look at summer, down in the lower left here. Most of the model projections, there's almost 20 that were used for this particular image, suggest drying in the summer. And of course, that's out of phase. Well, that's when our plants, our natural ecosystems need water the most. That's a major red flag. And we're looking at that more closely right now. In terms of a major impact in terms of the regions of the U.S., the southern Great Plains and the southwestern U.S. probably have some of the biggest challenges ahead, I think, without question. In the Great Lakes here, at least looking at the projections, we're relatively better off than that. But still, the fact that we have, even if we have more annual precipitation, a drier summer, that's a definite potential problem. Extreme events are also projected to increase. The number of days with heavy precipitation, we're already seeing that now empirically, and as well as the number of dry days. And this brings up another, almost a contradiction, and that's, I'm sure some of you have heard that's on the news, a trend or suggested projection for both more heavy rain events, more annual precipitation, but more droughts. How can that be possible? Well, it seems contradictory, but in reality what it suggests is, yes, we may have overall precipitation, but it's occurring on a more erratic basis. And that I think a verb is, or adjective is very, very important here. Erratic, precipitation becomes more erratic. It's certainly much more difficult to plan for. So it is possible to have both more heavy rain events and more droughts at the same time, and that's unfortunately what some of the models suggest, but the confidence in that is significantly less than it is for the overall mean precipitation. What about the Great Lakes? Obviously, it's a critical factor here in southeastern lower Michigan. There was a study done, two studies actually done in 2010. Catherine Hayhoe and colleagues, Jim Angel and Ken Kunkel, both published studies, and especially the Hayhoe et al. Study here, which is on the left, suggested significant decreases in lake levels with time. And of course, since we're already now at very low, abnormally low lake levels, by the way, with all of the recent precipitation this spring, I just looked at some data last night. Lake Michigan Huron has jumped 6 inches. And seasonally, we typically see an increase in the springtime, but it's usually only 2 or 3 inches. So all of that water, some of it was melted ice as well, but it's helped a great deal. We set a new record in Michigan Huron this past December and January. Erie was way down. It didn't set a new record, but it was close to the all-time record. But so this Hayhoe study was certainly of great concern about the levels of the lake. A more recent study by Brent Lofgren and colleagues at the Great Lakes Environmental Research Lab in 2011 used and I would call it a scientifically better technique of estimating evaporation. Evaporation is the major loss of water from the Great Lakes Basin, certainly from the lakes itself. And when he did that, what he found was a much, much more benign type of change. He basically had very little change either direction. And so right now, I would say that at least in terms of the latest results, the latest science on the Great Lakes level, it's uncertain. The jury's still out. But Brent's study was certainly more conservative than were earlier studies. What about impacts? And I want to just say a few things about this. These were taken from the recent Midwest technical report from the U.S. National Climate Assessment. These are impacts, and they're across a variety of different processes and industries, et cetera. But these are those that are considered very, very likely or high confidence. So we're looking at the most the most confident projections. One of them, the first one here, has an agricultural theme here, and that is basically says, well, overall, there will be a mix, both adverse and some beneficial impacts of climate change. And the first one basically for agriculture says if the climate is becoming warmer and wetter, and we're adding additional CO2 into the atmosphere, and that definitely is happening, and it will happen in the future, that actually is a positive, everything else held constant. And so some of the amazing increases, and technologically there have been huge increases in yields over the last several decades. Some of that in the upper Midwest is due to more favorable climate, that warmer, wetter trend that we talked about. That is projected to continue at least for the next few decades into the future, especially as more CO2 is added. But ultimately, depending on what happens with the extreme event frequency, we could see an offset of that or decline. The other big unknown or wild card at this point, something I've got research right now, what about pests? What about diseases? Exotic insects. We're dealing with those now. If a soybean plant is happier with warmer, wetter, more CO2, so are weeds. So are many weeds, and could potentially outcompete. So that's an unknown there. The second one here looks at our forests. We're seeing now changes in composition, the trees composition of our forests, and basically we're going to see a northward shift of boreal-type species and being replaced by more warmer tolerant species from the south. That's projected to happen in the future. The third one here talks about increased frequency of heat waves. That's a high likelihood, both the intensity and frequency, which of course is a public health issue. So likely to see more problems with that. The fourth one here deals with extreme rainfall events. We've talked about that a little bit. And flooding, in particular flooding. How do you engineer a way out of that? That has impacts on water quality and also on human health and infrastructure especially, and many of you are certainly involved with those types of decisions and planning. And finally here, the Great Lakes themselves, just like the forest species, with warming Great Lakes temperature, warming climate, we will undoubtedly see changes in species in the lakes. And there's a lot of work going on right now on this to try to understand that, because economically this is a huge factor for our region. And lastly, something we've seen certainly lately, with the ice cover decreasing on the Great Lakes, we have increased the length of the shipping season. And there's a caveat there, of course, if the Great Lakes are high enough to support shipping without dumping part of your cargo out. That's been a problem over the last several months. So, summarizing here, Michigan and the Great Lakes region, in essence the upper Midwest, have become warmer and wetter, but a lot of the warming has occurred during the cool season. There are a number of impacts associated with that, less ice on the lakes, warmer Great Lakes temperatures. Interestingly, projections for the future also suggest warmer and wetter, but the big caveat there, of course, is that the summers are forecast to be drier. That's a big potential problem. It could be coincidental that the projections are in agreement with the historical observations, but I think it's another piece of the puzzle. It adds a little bit of confidence to those projections and which way they're going. These changes have, depending on the process that we're interested in, a mix, some beneficial, some adverse impacts. It depends greatly on what you're interested in. And those changes are a big challenge to both human and natural ecosystems. And lastly, to leave, I think this is a paramount thing. We are shooting at a moving target. That makes our jobs, your jobs, even significantly more complicated. And so it goes without saying that as you set up planning and the ability to look ahead and to plan, it has to be dynamic. Almost unquestionably, these projections are just that. They're educated guesses or estimates. We're going to have to make changes along the way. We can no longer, I think, afford to look ahead and say, well, let's use a 1 in 100 year design criteria for this particular structure. It's not so easy, because we are, again, shooting at something which is changing or moving. And with that, I'll stop.
I want to say thank you to Dr. Andresen today for making the presentation.